So good afternoon, everyone. So I'm very happy to have Professor Thierry Dauxois visiting us for only 3 days. I don't know where do I actually start from. In order to introduce him, let me first do the academic part. So Thierry got his PhD in Dijon in France, and some of you must have heard about the place Dijon. It's famous for the mustard that you get. In Bengali we call it kashundi, particular brand of mustard that is. But it is also known for good physics. Okay, and probably you need to eat good mustard to do good physics. That I don't know. And then he was at various places. He was at Los Alamos National Laboratory as a postdoc. Then in Firenze also as a postdoc, as a Marie Curie fellow with Professor Stefano Ruffo. And then he joined the prestigious École Normale Supérieure, the Lyon, the Lyon part of the École Normale Supérieure, where he has been there ever since. He has been the director of the physics laboratory, the Laboratoire de Physique of the institute until recently. Probably you still are, but then in February next year, this year, next month, is going to take over as the vice president for research, which is a very prestigious position, a lot of responsibilities of the whole of ONS. And I must tell you for record that ONS has the distinction of producing, if I am not mistaken, the highest number of field medalists in the world and the highest number of physics, Nobel Prize laureates with, I think, 6 Nobel Prizes in physics. I mean, the ONS Lyon and Paris taken together, mostly Paris. Okay. So now, about his research work. Well, at some point I thought that maybe I should prepare something, but then I thought that maybe I don't prepare something, I just tell you whatever comes to my mind, because that's kind of an spontaneous way of expressing what I feel about him and his research and so on. So he has been working in the field of nonlinear dynamics. He's a very well-known person in the field. In our library, we have this book, Physics of Solitons, that he had written long ago with his PhD advisor. Michel was his PhD advisor. And he has also been working in the area of long-range interacting systems, made very important contributions to long-range systems. We have a book in the library, Physics of Long-Range Systems, written by him and others. And lately he has been interested in experimental aspects, internal waves and turbulence and so on, which he is going to talk about. So, I can go on talking about the academic part, but let me come to the non-academic part. So I have known Thierry, before I was a postdoc in Lyon, in his laboratory. And before coming to France, of course, I have always been fascinated by France, poetry, music, literature, food, particularly food, and so on. But I had always heard this thing about French people, that they are not particularly kind. Okay, so this was I was an outsider. I was coming from, in fact, at that time I was in Israel when I had the invitation to come there, and I was coming there, and that's what people have told me, that look, you're going there, maybe. But I must tell you, I should put it on record that Thierry is one of the most kind persons I have met in my life. In every hour of need, be it personal, be it academic, he was always there to help me in every possible way. I must tell you a few instances. One I remember quite well, that it so happened that I wanted to visit the lab. We had some collaboration going on, wanted to visit the lab. And it was December, and there's a local festival. Lyon is known for this Fête des Lumières, the light festival. And for some reason, all the hotels were booked, and I could not find an accommodation. So I told Thierry that maybe I come at some other time, because now that he said, no, not at all. So why don't you stay at my place? So I stayed at his place, and in fact, you know, this is something when you think about it, you may think that, oh, this is just a small gesture. I mean, what's so much in you know, staying at but you know, if you think deeply about it, it's not something that you know, we are used to. I mean, I've eaten at his place lunch, dinner and breakfast and whatnot, eaten and drank probably, yes, both together and separately, more number of times that like anyone whom I know of, any of my collaborators, including my PhD advisor. And there is one more instance that I should tell you, that it so happened that in Lyon I was staying in an apartment, and on one evening, you know, it was not really evening, it was late evening, I was back from my office, and you know, there was a code that one, you know, there was some code that one had to type in order to get into the apartment building, and then one had to take the staircase or the like elevator to get to my apartment. So it was like 10 o'clock in the night, and it was about the time, I mean, from the next day on, the French vacation period would start. And for French, as it is for Bengalis, vacation and holidays are an integral part of one's existence. Like food, vacation, okay, so once in a while you take off, and when you take off, you really take off. I mean, you don't, you know, go on vacation with mobiles and emails and this and that, okay. So, yeah, I was, you know, I typed in the code, and somehow the door did not open. So I had this experience before with ATMs, that sometimes things don't, you know, work out, and then what you do is that you give a break. I mean, you go for a walk, you come back and you type again, because sometimes the system doesn't like you to be trying one after another this thing. And I tried this couple of times and it didn't work out, and that, you know, somehow the door would not open, and then it would be the vacation period and the road was deserted, and you know, I could hardly see lights on in any of the apartments that I looked around. And it was not really cold, I mean, cold by Calcutta standard, but not by French standard. And I didn't know what to do, because you know, I'm just outside my apartment, and from the following day the lab would be closed, and I didn't know, I didn't have any relatives in France at that time, at whose place I can stay over, like overnight and so on. And it was getting late and I didn't know what to do. So then what I did was I called him up and I said, Thierry, by any chance do you know the phone number of the land, you know, the person who owned the apartment? Because he was in the same lab as us, Thierry and us. So he said, Shamik, what is the problem? So I told him that, look, this is the problem, that I type in the code and the door would not open, and I don't know what to do. So he said, okay, give me a minute, let me get back to Pierre, this person, and tell you what is the thing. And as it would happen, on that very day, I think Pierre's wife was giving birth to a baby, so they were in the hospital. And this guy could not simply leave the hospital. So when things conspire against you, I mean, almost every factors kind of conspire against you. So then he said that, sorry, Shamik, so this guy is in the hospital, and it's impossible to, he's very busy attending his wife, and so I said that no problem. So now that it's getting dark, so what I do is that I go to my office, and I have my desk. If not anything, I can lie down on the desk for tonight, and tomorrow morning we will see what to do. If we may break open the door or do something, call the police or something, but now it's too. So Thierry said that no, it's impossible. That for me, like it was okay. I mean, what to do? So it's impossible. So can you please wait there for 5 minutes? I am out for dinner with my wife, with a visitor that I have from MIT, Tom Pickup. So, you wait there, and I'm coming there with my car, and then we'll, drive you back, we'll bring you to our home, and for tonight you will be our guest. So I was, of course, like quite embarrassed, but then they both arrived, Thierry and Florence, and they took me off to their home, and the kind of hospitality that I received from him and his wife, I still remember Florence's reaction. So they were, he was driving the car, and Florence was sitting next to him, and I was sitting in the back row. And she looked at me and she said that, Shamik, we have a bad news for you. For tonight, our children are not with us. They have gone on, they are with their parents. So for tonight, you are going to be our child. So therefore, you have to listen to everything that we ask you to do. I said, okay, no problem. It would be an honor to listen to what you. And I still remember it, and I'll remember this incident till my last breath, because like as soon as I entered the bedroom, like they prepared the bed, and Thierry gave me a shorts, t-shirt and shorts that belonged to him for me to wear. Now you can see they're like orders of magnitude different, but still I managed. And he said that, look, in the morning, his wife said that, look, in the middle of the night, suppose you need to pee, then there's a table lamp here, so let's practice that. Suppose you you get up in the middle of the night, and here will be the light, so you switch it on. Here will be the toilet, and here is some water to drink if you get thirsty during the night. In the morning when I woke up, so Thierry was sitting outside. He said that the breakfast is ready. So let's have breakfast, and then I'll drive you to your apartment, and let's see how we can solve the problem. But of course, I was quite desperate to get back to the apartment, because I was kind of at a loss. I didn't know what to. So I said that, no, let's first find out. And then it, of course, worked out. Like, he has been extremely kind, extremely supportive, in academia. Like, for any small thing, any assistance that I require, any advice that I need on any, academic matter, one of the first persons, he's one of the first persons whose name comes to my mind. I would write him a message, and within a minute he would reply saying, dear Shamik, or bonjour Shamik, sometimes you write. And okay, so it's I can go on, but let me not go on, because you have come here to listen to Thierry. So I just give the before that, sorry, I forgot one important duty. That is to say that I would request Brahmachari Aditya to welcome him on behalf of the university, and to say a few words.
I would like to welcome Professor Thierry Dauxois, Thierry Dauxois to RKMVERI. So RKMVERI is the name of the university. It's the full form is Ramakrishna Mission Vivekananda Educational Research and Research Institute. So it's run by the Ramakrishna Mission. So that's a charitable, philanthropic, and spiritual organization that's about 123 years old now. So this university is named after Swami Vivekananda, who is the founder of the Ramakrishna Mission, and he's also in India. He's considered, perhaps I could say, the patron saint of modern India. So he lived in the late 19th century, but he was very modern in his outlook. So he was a monk. He was a Hindu monk, and so his idea of education was that education should combine the best features of the modern science, the West, the scientific inquiry and these features, along with the best features of the East, which is the traditional education, the respect, reverence for education, and spiritual values and virtues and so on. So even in our campus here, so we are trying to actualize those ideals. So in the campus too, we have departments like, so these are the mathematical sciences departments like physics, maths, and computer science. We also have Indian heritage school, within which we have departments like Sanskrit and yoga studies and so on. And there are other campuses where the university has agriculture and various whole range of subjects. So essentially, obviously, basic sciences like physics and mathematics. Yeah, mathematics will also come under basic sciences. So yes, all these subjects are where we try to give great emphasis on the research. So we are delighted to have such an esteemed visitor here. And in our department, in the area of nonlinear dynamics and statistical physics and so on, so Shamik is the main researcher, the person who does research in these areas. So, and apart from that, we also have people working in particle physics, cosmology, string theory, and experimental condensed matter physics, theoretical condensed matter physics. So whole range of areas are there. So we are all looking forward to what you would have to say about this topic. So a warm welcome to RKMVERI, and we hope this is the first in a series of several future visits. So yeah, yes. Oh yeah. So as a token of our appreciation for your visiting us, I have a small memento to give you on behalf of the university. So let me just. Who has explained very beautifully these ideas. And this photo is basically Swami Vivekananda, after whom the university is named. So Vivekananda. So I hope that you will be able to enjoy it. Okay. Thank you very much.
Is it okay? So I'm very pleased to be here today in Kolkata. It's my first time in Kolkata. I will be very pleased to give the seminar. I would like to thank deeply Shamik for his two kind words. It's very nice. Thank you very much for these two books that I will read. Recently, maybe I should say just one sentence about this. I like very much soccer. And I learned recently in a book that I was reading. I just spent 3 weeks in Chennai at IIT Madras, and I wrote some sentences about Vivekananda, who was fond of football also. So I was very pleased to visit your institution, and I was very pleased to see a football field yesterday when I arrived. But I should admit I was very disappointed because yesterday people were playing cricket on the football field. Okay, so thank you. So I will speak today about internal waves. I know that you are either physicists or mathematicians, and I will speak about fluid dynamics, but I am a physicist. So I will try to introduce this field, and I hope that you will be interested. This is the first point. So I apologize not to speak really on real physics, but you will see that this work or these internal waves can be useful to understand many concepts related to waves, and also from the mathematical point of view, they are nice objects. Okay. So I'm speaking in English, but with a strong French accent. I apologize for this. If there is a problem, just raise your hand, and I will try to make me to explain things clearer. Or Shamik will. His French is very good, so he will help me. So let's start. So I will start by discussing what are stratified fluids. Stratified fluids are fluids in which the density is a function of spatial variable, which could be the altitude or the depth, whether we discuss atmosphere or oceanic applications. And rho, the density could be a function of the temperature or the salinity, and this is why rho is a function of z. At the surface of the ocean, the density is smaller than at the bottom of the ocean because the temperature is different, because the salinity is different. And today, to be explicit, I will speak about stably stratified fluid, which means that the heavier fluid will be below lighter fluid. So there will not be convection phenomena that we are used to. Today, it's different. This kind of system is usually not taught in physics lectures, and poorly taught in fluid dynamics backgrounds also. So I will try to introduce this smoothly by presenting some simple experiments. First, the first experiment had an idea behind. This Norwegian explorer, his name is Fridtjof Nansen, who is very well known in Europe and in the world. He's one of the very important explorers. Had a boat which was very important, very nice. Its name was Fram. And this boat was able to go quite fast, 6 to 7 knots. And in some situations, especially in fjords, where you have river, especially in Norway, where river with pure water lying onto salted water of the ocean, the boat was not able to go very fast, and not more than 1.5 knots, for no reason. The surface of the ocean was flat, but the boat was stopped by somebody, or by someone, or by some animals, or some gods. We don't know. Actually, Nansen was not able to explain this. So the idea initially was to do the similar experiment in a tank, where we have fresh water on the top, that will be in red, salty water without any dye color, and very salty water at the bottom. Okay, so you have the heavier fluid below the very light, the pure water. So it is stably stratified. And the idea was studied a long time ago by Ekman, and the idea was to put a boat and to look what will be going on if you pull the boat with a constant force. Okay? And as physicists like to do, we will play with the different parameters. Either the tension, so what is this things here? What is the weight of the boat? What are the different depths of the depths of different layers? What are the different densities? But today I will show you only one single video to explain what is going on. So this is an experiment that has been performed by my former PhD student Mathieu Mercier and an undergraduate student, very good one, Romain Vasseur. So this is a boat. Initially it was a boat of my son, not Shamik, another one. So the boat, I took the boat to my lab without telling this to my son. And there is a small rope that you hardly see at the surface, above the surface, that will pull the boat with a constant force, okay? And the idea, you have pure water, very salty water, and you are interested in the behavior of the boat. So the point is to start and to look what's going on. So imagine that you are on the boat. You wouldn't be able to see these large amplitude waves that are generated. On the surface, there is no wave. There are no waves, actually. And you see that this large amplitude wave of the order of the depth is going faster, and at some point, the boat is trapped because of the waves below, and the boat is almost stopped. Okay? And then the waves go in front of the boat, and the boat can start again. Okay? So if you are in the boat, you are not able to understand what's going on. The water is dead. There are no ripples on the surface. Everything is below, and people were not able to understand what's going on. Yes?
It's relevant to what you're saying, but why is the density changing in steps rather than in gradient?
Because it's simpler. It is simpler. But I will go towards more realistic stratification later. Because if I show it, yes, but I will go in a few minutes. I will go. I thought it was simpler. So if you were in the boat, you do not understand what's going on. The water was called dead. This is called the dead water phenomenon. There is a second reason to call this the dead water phenomenon. We, all of us, maybe, as humans, when we do not understand what's going on, too often, it's a pity, but too often, we take guns and we kill the things that we do not understand. So Nansen, this explorer, was taking guns, trying to kill the animals who were behind the boat. So it's another reason to call this the dead water phenomenon. But actually, as you have seen, it was a wave, so using guns was completely useless, as in many cases. So the idea is that if you are in the boat, you are not able to see these underwater tsunamis. They are really like underwater tsunamis. And I will explain to you that the amplitude of these tsunamis are very important, much larger than the tsunamis in the surface of the ocean, and the amplitude can be very, very large. For example, this is a view from satellite images. You have Taiwan, Philippines, China. So India is on the west here. There are these big lines which are actually generated by the interaction between the tides and the bottom topography below the Luzon Strait. There is a bathymetry which is quite high. And because of the tides, twice per day, there's the formation of waves that are deriving or that are creating these huge waves that are able to propagate along the South China Sea. And these waves are actually signatures on the surface of the tsunamis, of these underwater tsunamis. So what you have to keep in mind is the perturbation is very small on the surface, but the perturbation of the underwater tsunamis are very huge. Typically, every day, there are underwater tsunamis, and the amplitude is 200 meters, 200. Okay, so it's a very, very, but as we will see, they are very huge amplitude, but the velocity, the period are quite large also. These waves are very important for many reasons. For example, waves are following these waves because the plankton below at the depths or in the deep ocean can be taken towards the surface, and so it's very good food. Indians like very much food, French, but whales also like food. Okay? So it's very important. It's also important from the biological point of view because there is a coral reef on the east of this island, which is provided by very good planktons, and for the coral it's very important. So there is a very nice coral reef in this region. So I will speak about these internal waves, but as you asked me 2 minutes ago, I will now consider stratification, which is more realistic. And instead of considering this simpler case, I will consider linear stratification. So I will have pure water at the top and very salted water at the bottom. You can understand the physical mechanism behind these waves by considering this simple slide in which you have a 2D slice of the ocean. So this is the gravity is vertical, and so I will call this spatial variable x, and the vertical one z. Okay? For most of the talk, the word will be 2D. Okay? Because it's simpler, and I think it's a good introduction. So let's consider a fluid particle at a given depth at density rho naught. If you move the particle up, you see that it is surrounded. The particle is surrounded by a density rho which is smaller. So there will be a competition between buoyancy and gravity. This is what is called the Archimedes law. And this fluid particle is heavy, or heavier than the fluid around it. So it will go down, and there will be an oscillation that will end up finally because of dissipation. And the typical frequency, n, its square is directly related to the gradient of density. So if you have a fluid which is homogeneous, not stratified, d rho dz will be 0. So if you move a fluid particle up, it will stay there, okay? Because it will be surrounded by the same density. This value of n, this value of the frequency, is called the Brown-Weissaler frequency or the buoyancy frequency, which it has been derived by these two meteorologists between the two world wars. Let's put numbers. We are physicists, or at least I am physicist. Typical value of the period, 2 pi over this value of n, is typically 30 minutes. So it's a slow process. They are not very fast. In the laboratory, as you will see in a minute, the typical period is 10 seconds. So there are large amplitudes, typically a few centimeters, that you can see in the lab, but they are rather slow. Okay? So it explains why I was educated as a theoretician, but we can do experiments. Actually, you will see that most of the experiments were done by my very good PhD students, but we can do this experiment also. And this phenomena is at the origin of internal waves that I will describe during the talk. So I will give 2 slides with analytical formula to show why these waves have very strange properties and why for a nonlinear physicist these waves are quite important. So if you do not have a very deep background in fluid mechanics, it's maybe a bit too fast, but you can forget it, and I will come back to simple ideas in 2 slides. So we will consider the fluid as being incompressible. It's an excellent approximation for the ocean, And we'll consider the Navier-Stokes equation that is used for basic fluid dynamics. So with the time derivative of the velocity, there is a pressure term, there is a dissipative term, and that there is a term where B is the perturbation with respect to the initial the density evolution as a function of Z. This is called the buoyancy term. This is the term due to Archimedes, explained by Archimedes. And there is the equation due to the mass conservation, which is written with B and not the density as we are used to, but this is the same. This is where we can get the Fick equation or things like that. So if you are considering the system as being 2D with the x horizontal variable and the vertical z, it is very well known that you can introduce a string function psi and write the two components of the velocity field as the derivative of this scalar field psi. So you replace two components by one single field psi. And then from this set of equations, you derive two different equations for psi and b, but which are coupled. You see that you have b and psi here, and you have a b here. So there are two equations which are nonlinear. This is the quadratic terms that are coming from this nonlinear term, the quadratic term of the Navier-Stokes equation. And here it is called the Jacobian, for those who are not familiar with this notation.
Psi is what here?
What?
Psi is what?
Psi is a string function.
What does it represent?
Physically, it's difficult to say, but its derivatives are the component of the velocity field.
Like, is it because divergence of grad is 0? So
Yes, you can. You can use it.
Divergence of u is 0, so you just take u
Yeah.
component.
So if you combine everything, at the end you have some blue terms in blue, some linear terms in blue, some terms, a term which is due to the viscosity, and some nonlinear terms. I will describe the effect of the different terms one by one. You will understand what's going on. So let's consider the linear approximation. This is always the first approximation that we are used to do in physics. So this is an equation which is, of course, linear. And you see that you have the spatial array. This is a Laplacian, or the nabla square. So you have the spatial variable at the same order for the two terms. So it's clearly different from the D'Alembert's equation, which is the wave equation for acoustic waves. In that case, it's different. Let's look for plane wave solution. This is what we are used to do when we do electromagnetic waves or optical waves. We look for solution with the exponential of I k r minus omega t, where k is a wave vector. The wave vector, because we are in the vertical plane, has two components, L and M. And what is important is to consider this angle theta between the k value and the vertical defined by the gravity. So you plug these ansatz into this wave equation, linear wave equation, and you get that you get a dispersion relation linking omega as a function of the wave component, but you see that it is directly linked to n sine of theta, n being the Brown-Weissela frequency that I introduced 2 slides ago. So because the system is linearly stratified, n is constant. So if you give me omega, a perturbation at a given frequency, for example, tides, or if you move an object in a stratified fluid, you know n, you know omega, which is given, and it means that waves will propagate at a given angle theta. Let's keep this in mind. So the second point, if I keep only the linear terms in the second equation for the mass conservation, you see that B, the buoyancy, is directly linked to psi. This is the second point to recall. So let's look what's going on in a typical experiment that we perform in our lab. This is a tank which will be linearly stratified. Here is the gravity, and we have some plates which are oscillating vertically at a given frequency omega. So there is a spatial excitation, but what is important is that each plate are oscillating at a given frequency omega. So they will excite waves that have to follow this dispersion relation. So the typical image is, video is what you get here. You see that almost immediately, this is so it has moved, I don't know why, but the generator is here. And you see that you are able to excite waves along this direction with different colors, which are actually the phase. So using the definition of the group velocity and the phase velocity, we know that the energy is emitted in the direction of the group velocity, and you see that it is emitting along with an inclined beam, which is inclined with an angle theta, which is given by the frequency omega of the oscillating plates. But the different colors being the phases, it means that the phase velocity is orthogonal to the group velocity. So this is something which is completely unusual, but actually that you can get directly in 2 lines by the calculation of the phase velocity and the group velocity of this dispersion relation. So it's a proof, experimental proof of something that you can predict theoretically.
So like in a given direction, if I want to excite some modes, I have to choose omega according to the definition.
Yes. Actually, you choose omega, and the waves will be propagating in only one direction. So it's completely different from the surface waves. If you have surface waves, if you excite with a given value of omega, you will excite concentric waves with a given wavelength, but the waves will be going in all directions. Here it's completely the opposite. You excite a given omega, you will excite waves in 4 different directions, so it's not isotropic, but the wavelength is completely free. You see that the wavelength is not appearing into this dispersion relation. So it's very different, okay? Okay, but the equation initially was nonlinear. So there are some nonlinear terms on the right-hand side that I would like to consider. Let's consider this plane wave solution. Because it is quite simple, it's possible to compute the Laplacian of psi, Laplace square, and it is nothing but minus k square psi. So here you get this simplification that g psi, Laplace square psi is this value which is 0. So this nonlinear term is 0. The second term of these nonlinear terms is figuring b as a function of psi. So again, you have g b psi, which is g psi p psi, this prefactor, which is also equal to 0. So you get this very interesting result that the right-hand side for nonlinear terms is also 0. So plane wave solutions are not only solution of the linear approximation, but also of the nonlinear approximation, of the nonlinear full equations. So for somebody who is used to nonlinearity, to nonlinear physics, it's really unusual and it's quite interesting. And this is one of the main interests for me initially to play with these waves. But being a solution, for those of you who are mathematicians, it's quite clear. It do not mean that it is a stable solution. And we will see that they are not stable. And actually, I can go back. I was careful to, if I go here, I start again the movie. Initially, you are generating a very nice beam, but you see after some time that the beam is disturbed. Actually, the waves the beam is unstable, and the solution that we derive analytically is not stable. We get it here. So let me come to the analysis of this beam. After some 50 periods, we see a destabilization, not a very clean beam as it was initially. And actually, it's possible to do the Fourier transform of this movie. If you do the Fourier transform, you have a DC component, but you have the more important peaks of this quantity, which is telling you what is the spectrum content of this field. You see 3 different frequencies, 3 different peaks, in which you can see that omega naught, which is a frequency that you generate, that you are using within this, using this generator, can lead to the generation of 2 subharmonic waves, omega 1 and omega 2, and the sum of these 2 frequencies is giving omega naught. Knowing these 3 frequencies, it is possible to filter the movie at these 3 different frequencies. Okay? And actually, it is possible to use this Hilbert transform. So for those of you who have some mathematical background, it's possible from the field, the velocity field, or in that case, the gradient of the density field as a function of time and x and z, it is possible to get the phase of the 3 different beams that are appearing when you filter at omega naught, at omega 1, or at omega 2. So the first remark is that you see that the 3 different beams are inclined with a different inclination. It is expected because a different value of omega means a different value of theta. So clearly the inclination is different. The second point is that you see that the periodicity, the spatial periodicity is different for the three different beams. Actually, because it is a phase, the phase is k, it's L x plus m z minus omega t. If you differentiate with respect to x or z, you can get the two wave numbers of the wave vector. So actually, it's quite clear that it is orthogonal to the phase planes, and you get three different wave vectors which are different lengths, different angle of inclinations, because different frequencies. And you can check experimentally that you have this relationship, actually, k naught, the initial wave vector that you are sending into the system, is giving rise to two subharmonic waves, which have not only this temporal spatial resonance condition, but temporal resonance condition, but also this spatial resonance condition. And this is called the triadic resonance stability. It is a very nice system to check this triadic resonance stability, which is due to the quadratic nonlinearity of the Navier-Stokes equation. So it was an introduction, but I will continue and go on and show you something which is quite unexpected again. So the name is internal wave attractors. So the idea is quite simple and can be explained in 2 slides quite easily. And then I will go show you the experiment. So let's take an internal wave. We have this dispersion relation where omega is linked to this angle theta. So if omega is given and n is given, theta is given. So if you have an incident internal wave going toward the vertical plane, you will have a reflection, and it has to follow this dispersion relation. So the angle with respect to the gravity or with respect to horizontal will be the same. So it's nothing, it's not strange. It is a Snell-Descartes reflection as we have for acoustic waves or optical waves. No surprise. Things are much more interesting if you consider now an inclined wall with an angle alpha that will be quite important. Let's consider the same initial beam in blue. In that case, you cannot take the Snell-Descartes reflection because this red beam is not following this dispersion relation. So what you would get for optical waves or acoustic waves is not what you will get for internal waves. In such a case, you have to follow this dispersion law because omega is the same before and after reflection. So actually, the angle is the same, even if the wall is inclined. Okay?
Wall is inclined with respect to what?
To the vertical, with respect to G. Okay?
Because
gravity is always downward. Okay? But it could be like that if you prefer. Okay? So the point is to have a value of alpha. Things are even more interesting if you consider a beam. Now you see that the pattern that you get, the picture that you get, you see that the widths before and after reflection are different. You see that the width is larger before than after reflection. So because you have conservation of energy, if you forget at least viscosity, it means that the energy density after reflection is larger. Okay? So it means that you have a system which is dictated by linear dispersion relation, in which you have a transfer to small scales, you have energy focalization, and you used only linear physics. Okay? So it's a linear transfer to small scales. For people who are interested in turbulence, for example, it's a very interesting phenomena because everything is due to linearity, while usually it's due to the nonlinear terms. If you get you can go beyond. If you consider only one wavelength in width, after reflection you will have also one wavelength, which will be smaller. So it's really a transfer to small scales, and this is what we call linear cascade in wavelength. So the idea, using these reflection properties, Leo Mas, a Dutch collaborator, very smart person, had a long time ago a very nice idea in which he was considering a tank in which you have 2 horizontal walls, 1 vertical wall, and 1 inclined wall with this angle alpha. And the idea would be, the proposition by Leo Mas was, if somebody is able to move the vertical wall at a given frequency omega, that will generate frequencies at a given frequency omega, so that it will be propagating with an angle theta which will be given. And after reflection, you see that using ray tracing, we will eventually end along this perimeter, which is a limit cycle, and it is called an internal wave attractor, because if you take the very same domain, you excite waves with the same frequency. You remember that you have the possibility of having 2 plus or minus theta. Then you will end up, after a transient, you will end up along this same limit cycle, and you will get, actually, for any point excited on the left wall at a frequency omega, all the energy will eventually end up along this attractor. So for people who are used to nonlinear physics, it's very strange, because here I'm still using only the linear dispersion relation, while limit cycle is a prominent word for nonlinear systems. But actually, you can say that the nonlinearity is hidden in this reflection law, but this is an idea that I will not discuss further right now.
So this alpha is controlling the density?
No, not at all. No, alpha is a geometry. The density is inside the tank.
No. Alpha is controlling the density after the reflection.
Yes. Yes. Exactly. Yes. You are fully right. So this system is nice because depending on the value of omega, you change theta. You remember the theta of propagation. And if you have, if you take different angles theta, different frequencies, you will get attractors with 2 reflections on the top and 1 on the on the left, or 1 on the top, 3 on the left, or all the energy will end up in this corner and will be dissipated, or you can get something like which is almost ergodic or ergodic-like. Okay, so it's a billiard. I don't know if you like billiard in Kolkata, but it's a billiard that mathematicians like to play with, but also any person.
Just to understand clearly, this is a fluid cavity which has boundaries on all 4 sides.
Yes.
One of which is slant.
Yes.
And there is an attractor solution that basically bounces around and keeps.
Yes, precisely. So I will introduce a concept which is not too complicated, but maybe not known by everybody within the audience. So I did this slide. The concept is the concept of Lyapunov exponent. Let's imagine that we have 2 different trajectories, 2 orbits, which are initially closed. For any dynamical system, we can study the evolution of this distance between the 2 different trajectories. And typically, in many systems, the evolution is going like exponential lambda t. If lambda is positive, so this lambda is called the Lyapunov exponent. If lambda is positive, it means that the distance is diverging, and actually this is the case of any chaotic system. If lambda is negative, it means that the 2 trajectories will be closer and closer. It means that they will converge, and the system will be stable. Okay, this is a concept that is very important for many applications and even from the mathematical point of view, but this is the only result that I need today. So, this is a picture that is a resume. So this picture obtained by Leo Mas and his student Franz-Peter Lam, which is a bit complicated, but that I will need later. But I will try to be pedagogical in the sense that I will tell you only the main important things. So you have on the left, on the vertical, you have the frequency. This is the forcing. H is the depth of the fluid, L is the length of the tank, N is given. So here, by changing omega, you will go up and down. Horizontally, you have the geometry of the tank. H and L are still given, and you have only the value of alpha, which is on the right-hand side. And here, they were plotting the value of the Lyapunov exponent. Actually, in all cases, the Lyapunov exponent were negative, which means that 2 trajectories which are close will be even closer later. Okay? So it means that you will converge towards this attractor for any values. But the colors, actually, whether it is white or black, means how fast it will go towards the attractor. When it is white, it will go very fast. And actually, you have different regions. This tongue, this white tongue, is a 1-1 attractor. It means that here, if you are able to excite within this tongue, you will get a 1 attractor, 1 reflection on the top and 1 on the left. And actually, by moving from up to this bottom limit, you will get from one attractor elongating in this direction to the other one elongating in this direction. And then you have other possibilities. You recover the 1-3 attractor. Here you have some ergodic-like behavior. Here you have a 2-1 attractor, and so on. So by doing one experiment, you can excite, by doing an experiment at the frequency omega and at the value of alpha given, you could expect to see this attractor in a lab. So this is an experiment that has been performed in our lab, where we have a tank which is 2 meters long, 1 meter high, and there will be the oscillation of a generator with this profile at a given frequency omega and with a spatial cosine vertically. So the perturbation will be very small, 2 millimeters, that you have to compare with 2,000 millimeters horizontally. So it's a perturbation that you almost see experimentally, and the system is very thin in this direction, so it's almost 2D. So the fluid is stratified. The density is a function of Z. This experiment has been performed by Geraldine Davis, who just defended her thesis. And she was able to put the wave generator on the left-hand side, and she put also some isopycnals to show the lines of iso density initially. Okay? And everything is shined with a laser sheet, and you put some fluorescein, and it means that the density is the same along this horizontal line. And then you start the wave generator. So this is what you will see in a second. The generator becomes to start, so there will be the oscillation that you hardly see because it is only 2 millimeters. And then you wait. You wait some time, and maybe you start to see that quite easily you see the motion of the fluid along this line, okay? Because the energy will be trapped along this attractor. If you are inside, in the center of the, you hardly see anything. Waves are not there, okay? So it's like the dead water phenomenon before. You do not see anything. But if you are along this attractor, clearly it is moving, and although the perturbation is very small. All the energy will be focused around this attractor. So you can compare what was the prediction, the mathematical prediction, and the experimental result. And this is after 6, 12, and 30 periods. And this is the prediction. And you can check that the positions are quite similar, actually even quantitatively similar. But there is a big difference. The width of the attractor was infinitely small in the theoretical prediction using this ray tracing evolution. While experimentally, there is a width which is clearly finite. This is due to the balance between viscous damping, which would like to have very wide beams, and the focusing, which is trying to condense the energy. And this is why you have a finite value and not a zero value for the width. And you can check this. This is what has done Christophe Brosé in a small tank and in a large tank. This is only 40 centimeters. This one is 150. You see that the relative width is smaller because the system being larger, the viscosity is less important, and the effective viscosity is smaller, so it means that the width is smaller.
Why wouldn't we see anything if alpha is 0? Do we have such stable solutions?
I will come back to this. You are very smart, and you are always a few slides in front of me. I will come to this point in a minute. So it's possible to do 2-1 attractors. In that case, you have 2 reflections on the top and 1 on the bottom. And you can do and play with this kind of attractors. The point is that because of the viscosity, the perimeter being larger, it's when you increase the number in front of the first, the first number, it is more and more difficult to see it experimentally. Okay, this is the introduction of the internal well attractor. And I will discuss now a very simple experiment that has been proposed by Geraldine herself. And this is a very nice idea that is quite typical for physicists that you will understand immediately. So the idea was the following. if you use a tuning fork, which is very useful to musicians, you know that if you kick this system, you will emit a pure musical tone and a few harmonics. I was in Chennai attending a concert with Veena. I'm sure that before he was using this kind of system to have the good tone. So the idea was the following. We will do the same thing using the same experimental setup. So instead of kicking with such an object, we will start with initially the red shape, and after a very short time, we'll stop the generator vertically. So it's like a kick. And you expect to see whether you will get something similar to the tuning fork. So the delta t is typically 1 second, very short. Actually, it's a fraction of a second. So now, because of the kick, you excite all frequencies a priori. And you would be interested whether you will have what kind of response will give you the experimental setup. The experimental setup for that we were using for the attractor, of course, not for the tuning fork. So now you excite all frequencies because you have alpha, which is given. This is the angle of the slope. So this is vertical line, but you can excite all frequencies. So before I was moving the generator with only one frequency. Now with this very short excitation, you can excite all points on this vertical line. So it's very, very, very nice, and it's a clever idea also from the PhD student point of view, because it is you do the vertical line immediately. You don't have to do all points, and instead of waiting for the stabilization of the phenomena, it's a very short experiment. So during a PhD, you have to go fast. So she was very smart to propose this idea, and you will see that it's a very powerful idea. So I recall that depending on the position, you have either 1-1 attractor or 1-3 attractor or 2-1 attractor. Okay, so using the vertical line, you may expect to see what is the behavior of this experimental setup.
So you have to ensure that the kick is really small.
Yes.
Because otherwise the whole diagram may be changed.
Yes, you have to be within the linear regime. Very good. Alors, to come back to your point, if alpha is equal to 0, it means that you are on this line. Okay? So I will come to this later. So using a unique experiment, we will test all frequencies. So for alpha equal to 0, we'll be on the right-hand side, vertical line. And in that case, the domain is a rectangle. And then you can do everything analytically, and you have the modes that are expected. So this is the dashed different colors, which are actually equivalent to the musical tones that were emitted by the different harmonics that were emitted for the tuning fork. And this is the same thing for the rectangle. Okay? And if you are able to compute the velocity field using PIV measurements, you can plot this quantity, and you recover some sharp peak precisely where the theory is telling you that you will get some discrete modes. So we have to remind that on the right-hand side, on this right vertical line, you will get different discrete modes which are predicted by the rectangular geometry. But when alpha is non-zero, we don't know what will be the response. Or actually, we didn't. So let's consider a value of alpha which is different from 0. Then in that case, we are on this vertical line. We excite all frequencies of this vertical line. D is smaller than 1. And this is a typical experimental result that was possible to get. So we see broad peaks that are located along, for example, this square corresponds to this tongue. This blue line corresponds to this white tongue, and so on. So we get broad peak and not anymore discrete ones, which are located in the center of the tongues, the main tongues, and in between you have a very small signal that you are not able to really see using the experiment. So this is an analysis of this result in which we had superposed the different experimental results obtained for different value of alpha. So these are vertical lines, and these are value. This is a case where alpha is equal to 0, so the rectangle, and then this is a trapezoid with different value of alpha. And this is a typical result for one value of alpha. You have different peaks, and for example, these three frequencies, omega C, omega D, and omega E, which are belonging to this first peak, you can use these different frequencies to filter the result, the experimental result, and you obtain that for omega C, for this value, you get a 1-1 attractor. For omega D, which is almost the top, you get almost a squared attractor, and omega E, you get this elongated in the other direction. So actually, moving along this line, you are able to see that the response of the system is telling you that we have the attractors. These are the modes that are generated by the kick. Okay? So this is the equivalent of the sine and cosine that we get for the rectangular geometry. If you go along this peak, this broad peak, it means that you are along this band. You get the same thing, different forms of the 2-1 attractor because you are in the 2-1 tone. So you see that these attractors are not only very nice mathematical objects, but we can see that they are very important. They are appearing as soon as we excite the system using kicked forcing. There are also nice prolongation of this idea of resonance and quasi-resonance that you can see in the work by Yves Collen-Verdière and Laure Serremont, which is a nice mathematical description of this experiment. So to conclude, I would like to go beyond the linear regime. This is what you wanted as a good nonlinear physicist. You wanted me to check what will be going on if I increase the forcing of the system. So this is what Geraldine has done just for you, Shamik. She increased the value of the amplitude and look what was going on. So in that case, the forcing is 12 millimeters instead of 2 millimeters. So now you are able to see the oscillation of the generator, and you see that you are able to see the attractor, but you see also in that case some overtuning effect. Some lines which were below becomes above. This is what we call overtunings. And as you see also there is some mixing. In that case, the density will be mixed locally, and it is clearly the nonlinear regime. You are exciting too much. And actually, if you are careful, this was the first three pictures that I showed before, which were corresponding to the predictions. But after a longer time, you see a perturbation of the attractor. So I didn't tell you, but you see that you have the attractor, which is this is the amplitude as a function of you are able to see that the amplitude as a function of the distance is decreasing. This is due to the dissipation, to the damping. And after, you have the focalization that comes back to the very same amplitude. So you have dissipation, focalization, dissipation, focalization. So this line, its amplitude is the largest, you see in this value. So it's where the instability is taking place because the amplitude is the largest. And actually you can check, and we have done this in this paper, that actually you have an instability of this beam, which is the triadic resonance instability. It means that the attractor is a solution, but it is destabilized when you get towards too large amplitude, and you get the very same conditions for resonance. And in that case, because of these generations of two subharmonic waves with two different frequencies and two different wave vectors, we have a cascade whose origin is the triadic resonance instability. So it's clearly a nonlinear cascade in wavelengths and in frequency. So this is almost the final slide. This is an experiment which has been inspired by some nice studies of vibrating plates. So in that case, we took the very same experimental setup with an amplitude of the forcing which go from 2 millimeters towards 12 millimeters. And we will increase the amplitude smoothly, slowly, toward this 10 millimeters. So we'll start from the linear regime, and at the end we expect to get the nonlinear regime. And we look to the velocity field, actually the horizontal velocity field, in one point of the system at x naught and z naught position. Initially you have a very nice oscillating behavior. Then you see some destabilization, and at the end you would say that it is like a chaotic signal. If you do an image initially in this domain, you get such an attractor. If you increase the amplitude, you see that you can see an attractor, but it is not very clear. And in that region, clearly the attractor is not really present. You have a lot of waves that you cannot really see where is the attractor. It has been destabilized by this triadic resonance instability, and it is something much more complicated. And to get a clear view of what's going on, the idea is to study the frequency content using this complicated integral, which is telling you what is the frequency spectrum as a function of time. So initially, we force the system at a given frequency omega naught, which is this value. And then, when we increase the amplitude, we see the appearance of two different frequencies, which are omega 1 and omega 2, whose sum is omega naught. So this is due to the instability, the triadic resonance stability. And at the end, you see that we have a much richer spectrum. So we have the linear regime, we have some instability, so we have two subharmonic waves, only 1, 2, 3 waves. And then we have a cascade of triadic resonance wave interactions, and above we have some very rich spectrum, and actually mixing, as we have seen in the small video that I just showed a few slides ago. So we have, using this experimental setup, something like a cascade in frequencies, clearly. We see initially we have only one frequency, which is injected into the system. And when we increase the amplitude, we see that at the end we have many frequencies. So we have all ingredients for studying different linear waves, or waves that are interacting weakly because the amplitude is becoming larger. And in this domain, clearly we will have some mixing, and we have some turbulent, without wave turbulence, but clearly nonlinear turbulence phenomena. So this is the final slide that I would like to conclude with. That is a recent result of the work by Géraldine Davis, Timothée Jamin, and Julie Deleuze. So actually, this is the evolution of the spectrum, the spatial spectrum, the wave number, as a function of time when you increase the amplitude from the 2 millimeters to 10 millimeters, from the blue to the red. So initially you have a decrease which is exponential-like, which is there is a good prediction for this that has been provided by Félix Beckett-Bazet and Leo Mas. And when you increase the amplitude of the forcing, at the end you have a spectrum that collapses, and you see that you get some spectrum which could be fitted by an algebraic decay with a low in k minus 3. And actually, we were able to show that changing the forcing, either we take a monochromatic forcing, omega, as I was just explaining, or we inject energy at a frequency omega within one of these bands, for example, in the band of 1,1 attractor. Then in all these cases, we get a spatial spectra which is compatible with the k minus 3 algebraic decay. Everything is not perfect. As we can see, we have almost a decade, not totally a decade. So this work could be improved, but it is the very first experiment in which we are able to show rather clear algebraic decay using internal waves. So it could be the first internal wave turbulence experiment. So I would like to conclude with this spectrum in k minus 3 that has to be explained theoretically, but that seems to be quite robust experimentally. So the take-home messages for you would be maybe the discovery of the existence of underwater tsunamis, these very large amplitude waves below the surface. The possibility to have internal wave attractor, this limit cycle that we have shown experimentally and discussed theoretically. Actually, it's possible to consider homogeneous fluid rotating. In that case, we could excite inertial waves, which are due to the Coriolis force. And in this system, it's possible to get the very similar idea of attractors, inertial wave attractors, and we are doing experiments like that also in the lab. And finally, we have seen that this setup could be used as a study of internal wave turbulence, which correspond to the statistical physics analysis of these weakly interacting internal waves. And there is now an initiative with different groups over the world to study wave turbulence, not only for internal waves, but also for optics, for gravitational waves, for many different, for BEC waves and things like that. This is the conclusion. This is the acknowledgements of the work done by Christophe Brozet to characterize attractors, and Geraldine Davis was the PhD student doing this kick experiment and the evolution towards internal wave turbulence. Julie Deleuze is an undergrad lady who worked with us on this question recently. Timothée Jamin and Hélène Scolan were two postdocs working on this problem. Hélène essentially on the instability of internal waves through theoretic resonance instability, and Timothée Jamin for the work about wave turbulence. And finally, my two colleagues, Evgeny Armaniuk from Novosibirsk, who spent 2 years in our lab, and Sylvain Jobot, who is my closer collaborator in Lyon, working on this question. Both of them were very helpful, and some agency to fund our research. I would like to thank you for your attention. Yes, it is guaranteed because when I showed this this plot, this plot, which is showing the Lyapunov exponent, tells you that, I told you maybe too fast, that all Lyapunov exponents are zero, are negative, which means that in all cases, for any value of omega and alpha, you will converge toward an attractor. So generically, you will get an attractor. But the value could be either rather large, negative but large, so the convergence will be very fast, or could be negative but small when it's black. So in that case, it will be difficult in the lab. So in that case, it will be difficult to see it because the conversion will be very slow. And because of the dissipation, the waves will have been dissipated before closing the perimeter. Okay? So from the mathematical point of view, you will always have attractors, but from the experimental point of view, it will be difficult to see this because the dissipation is too large in the lab. With? Yes. What with liquids? No. In principle, yes, but I think it's very difficult because you need something to reflect the waves above. So in the ocean, it's simpler. You have the surface of the ocean, and the internal waves are reflecting. They will be reflecting also on the bottom topography, so it's easier to have such a phenomenon. But you do not have mountains which on the top of the atmosphere. But you can get so stars are rotating objects which are stratified. So you have the possibility in some of the stars to have internal waves. And it has been shown that the possibility to get internal waves can be expected in stars, and people are using this. So this is another domain where you get such attractors. There is a very nice works by the group of Michel Riotor about this question.
Those peaks, how we can get it in practical, naturally?
In experiment or in the ocean, you mean? I don't know. You could imagine some explosion or some earthquakes, but this is not the point. The point is a physical idea to test the response of the system and to get, excuse me, you get in one very short experiment the response of the system for any value of the frequency. The idea was not to reproduce something which was going on experimentally. No, these are gravity waves, which are not gravitational waves. The words are different.
So this k to the -3, so is there an understanding of how can one go about understanding why it is k to the -3?
So there are some works on this. No works are completely satisfactory, and some mathematicians are working on this right now, but it is also possible and quite expected that this -3 will depend on the geometry, especially the dimension. So the experiment was 2D. In nature, it will be 3D. So this is why we would like to consider more realistic geometry in 3D to test if this exponent is robust or depends on the dimension, and also to have some theoretical prediction about it.
And this 2D was because it's basically gravity this way, and then you don't consider any dispersion in the...
Yes, because the tank is very thin. It's 2 meters long, but 17 centimeters wide. And the forcing also is... Yes. So omega would be, for example, the forcing due to the tides. And what I didn't say, just a minute, the dispersion relation is omega equal n sine of theta. Omega is equal to n sinus of theta. Theta is the angle. The sinus is, of course, smaller than 1. So omega has to be smaller than n. So you can excite waves, propagating waves, only for value below n.
Right. And I think all the density profiles you're taking is linear density profile.
In what I discussed today, except the very first experiment, but you were not happy, so I switched to the linear stratification. But we are considering nonlinear stratification. In nature, it is nonlinear, but it's an approximation. But any curve, or for physicists at least, can be locally considered as a straight slope. But there are interesting effects due to the nonlinear stratification, and we are considering this.
So
yes.
the motion of everything is to some approximation linear works.
Yes. We are physicists. We start with simplification, and then we go towards more realistic. But you can understand, the linear dispersion is omega is equal to n sine of theta. If n is varying, is not constant, if omega is constant, it means that theta will change. So if n, okay, you see, omega is equal to n sine of theta. If n is constant, if omega is constant, theta is constant. But if n is slowly changing with z, it means that theta will change with z. So instead of propagating linearly, there will be a bending which will be small because of the value of n which is changing. So you can do some WKB approximation of this, and it works quite well.
So you say something about the size of the tank when we can neglect the viscosity, right? So
No, I didn't say that we can neglect the viscosity. I said the effect of viscosity is smaller when the tank is larger. There is a quantity which is called the Reynolds number, which is comparing in the Navier-Stokes equation the term due to the nonlinearity, the U grad U, with the term due to the dissipation. So when, and in that, at the end you get this number is the velocity field times the size of system divided by the viscosity. So we are playing, we are using water, salt water, but water. So the density is known and you cannot change it easily. So you have the possibility to increase U or to increase L to change this value of the Reynolds number. So what I was saying is that by increasing L is as if you decrease the viscosity.
Any other questions? If not, then let's thank Thierry for this very interesting